All right, catalysts. That's our final topic from chapter 6. And what do catalysts do? They increase reaction rate. So let's think about that with a reaction. So we have an exothermic reaction. We have the starting materials here and the products down here. That catalyst is going to increase the reaction rate. So what is that going to impact in our reaction coordinate diagram? The thing that determines how fast a reaction happens, what is that? So think about that for a second. Is it where the product is, where the starting material is? No, that's more relevant to KEQ. If we look back in our notes to where we talked about KEQ, KEQ describes the relative amounts of reactants and products at equilibrium. That was back on page 6 of our chapter 6 notes. So KEQ is at equilibrium. So the spot where this is the same. The spot where the starting material is also the same. So whether or not it happens fast or slow, those things stay the same, so KEQ would stay the same. So why would we need to increase a reaction rate? So say that this reaction was favorable, it's exothermic, which that's what it means when it's favorable. A favorable reaction is exothermic. So what's a reaction that you probably heard about in Gen Chem like this? Well, carbon itself, just carbon by itself, elemental carbon, has multiple versions of itself. So graphite is a form of carbon, so that's what's in your pencil when you're writing. But also diamond, so what is often given as a wedding engagement ring thing, that is also carbon, and it's actually a more stable version of carbon. So if the diamonds, so we can put this as diamonds, if this is way more stable than the starting material, graphite, that are both versions of carbon, why isn't there way more diamond around and way less graphite around? Well, the reason is that the reaction going from the starting material to the products is really slow. And what that means is that it has an enormous energy of activation. So we'll actually we'll go up to the top of this board. So the EA, remember, is where we start at our starting material, EA, and so yeah, it's to the top, to that transition state. The EA goes from the position of the starting material up to the transition state. So why don't we have a bunch of diamonds around? Because that activation energy to get to the diamonds is really high. So what does a catalyst do? It increases reaction rate, and it does that by decreasing EA. So if we take the same reaction, we add a catalyst, and no one's found a good way to do this as far as this graphite to diamond analogy. But if someone did, they would essentially take that same energy level of the starting material, the same energy level of the product, nothing changed there, but instead of having an activation energy that's way too high for the reaction to appreciably go, the activation energy with the catalyst is more reasonable. So this is the EA with a catalyst. So what does a catalyst impact? It impacts EA. Delta G stays the same. This difference, this is the delta G difference, which is sometimes written as delta H. This delta G difference with or without a catalyst remains the same. And how does delta G relate to KEQ? It's a direct comparison. We went through that a few pages back as well. So essentially a catalyst, all that it does is it speeds up a reaction. And it speeds it up in both the forward and the reverse way. So that's essentially what a catalyst is. Another aspect of a catalyst is it's not consumed in the reaction, it's used and then it's reformed in the same reaction. So we'll see a lot of types of catalysts in organic chemistry, especially in organic chemistry 2. So if you stick around there, we'll see a lot of catalytic acids and bases. So that's what a catalyst is. All right, finishing up chapter 6, on the bottom of page 11 of our notes, we just have some kind of questions to wrap our heads around. So the first one is, which of the following impact rate? And we just have a lot of different kind of terms that we've talked about throughout the chapter. So I think this is a good time for you guys to pause the video and tackle this first one. Which of these things follow rate? So, all right, you already paused it. You decided for yourself. Let's see how it goes. So, do delta G and delta H impact rate? No. What we just saw in the last video was that where delta G and delta H are says nothing about activation energy. And if it's a really favorable reaction, it's really downhill, but it has this enormous hill to get over, it's still going to be extremely slow, the rate. So that will not impact rate. Energy of activation is the most direct thing related to rate. Higher would be a slower rate, lower EA would be a faster rate. But temperature also impacts rate. Remember, it's all about molecular collisions, right? And if there's more kinetic energy, then there's more molecular collisions. And the temperature, the higher temperature means things are moving around faster. So temperature would also impact rate. What about concentration? Yes, that would also impact rate. If there are more molecules to react with one another, they will react faster. KEQ, remember KEQ describes the system at equilibrium. So the number associated with KEQ has nothing to do with how fast the reaction happens. It's just describing the reaction once it gets to completion. What's this K? This one's small. That one over there, F, is big. This is the rate constant. So small k is the rate constant. And remember, rate equals the small k rate constant times the concentration of the reactants in that rate determining step. So we'll just say A and B, and then we'll put both A/B in the rate determining step. So what goes into the rate constant K? The rate constant changes depending on what the temperature is. If the temperature is higher, K is going to be a larger number. EA is also related to K. A lower EA, a lower activation energy, would mean a faster rate, so that would mean a higher K value. What about catalysts? How does that impact rate? That also increases rate. So all of those things impact the rate. The catalyst would also increase the size of the rate constant K, so that the number associated with that would be larger if we had a catalyst in the reaction. So essentially we have to remember that the things that describe where the energy of the starting material versus the reactants, those things are not important with rate. That's just telling us where our starting material is, where our product is. That's what is defined by those things. All these other factors do impact rate. So, next question. What is favored at equilibrium? So once we reach equilibrium, what do these terms mean about what is favored? Are the reactants favored? Are the products favored? Or can we not tell depending on what the values mean? So again, a good spot to pause the video, decide for yourself. Does this KEQ value mean the products are favored or the reactants are favored, etc.? So boop, you paused it. You're back. KEQ, what does that equal to again? KEQ equals the concentration of the products or the reactants. And obviously, often I say starting material instead of reactants. It's faster to draw. So if KEQ is 0.9, that tells me that the starting material is larger than the products in this equation. So what that means is that the starting materials, the reactants, A, are favored if KEQ is equal to 0.9. What about this one? If delta G is equal to negative 200 kilojoules per mole. So that's a negative value. Delta G, when it's negative, that means energy was released. It's exothermic. So this negative means it was exothermic. And when something's exothermic, that means that the products were more stable than the reactants. Products more stable. And organic chemistry and all chemistry and really everything, systems want to equilibrate until they are most stable. So if we're going down in energy to a lower delta G, we are going to be going to a more stable position, and that's going to favor the product. So this was B, products are favored. What about delta S? So delta S here, remember delta S is entropy. Delta S is entropy. And how is that related to if a system is favoring the products of the reactants? Well, delta G equals delta H minus T delta S. So this is 40 is the value for delta S. That's a positive value. We're subtracting a positive value. It would make delta G more negative, but we don't know, right? Because we don't know what T is yet. We also don't know what delta H is. So this would be kind of like can't tell. If this one was fully dependent on just delta S, this delta S favors product formation, right? Because a positive number here makes delta G more negative. So positive entropy, we'll put that down here. Positive entropy makes, it's actually positive delta S makes delta G more negative. And that favors products. But without knowing what T is, without knowing what delta H is, we can't really say if delta G is going to be negative or positive. So we can't really say if the reactants or the products are favored at equilibrium. Last one. A reaction with a fast rate. What is favored at equilibrium? Rate has nothing to do with if the products are favored or the reactants are favored. We could have a low rate, but we're actually going uphill in energy. So usually when we draw these reaction coordinates, the products are more stable than the reactants, but we could have a reaction coordinate where actually the products are higher in energy than the reactants, but it's just a really low EA barrier to get there. This is a low EA. And in that case, it's a fast reaction, but the products are not favored there. So again, 4 is C. We can't tell. That just tells us that it's a fast reaction. It doesn't tell us if it is favoring the products or the reactants. So that finishes up this chapter, full of terms and stuff to help us understand reactions when we really get into specifics in Chapter 7. So let me know if there are questions, and I will be available. See you later.